we start a new, last but not least topic. We start magnetism. And you know, today is a busy day because you will get a lot of interesting talks. First of all, it will be Dirac ceremony, and Peter Zoller and Eckhart are going to give 2 lectures, and then there will be talks of awardis. So the prize is given for quantum information processing, and you will see top people today really. So, therefore, I strongly suggest that you attend everything. I don't know about this session in Trieste downtown. It would probably be, which is going to be after 6. Well, this is public. There will be, it's public event. There will be Italian representatives and people from university, so everything will be synchronically translated to Italian. So this is up to you to decide, but I would strongly recommend you to attend the afternoon sessions. So lecture number 13, and I deliberately change a little bit order of lectures. Typically I start with some lecture devoted to Curie-Weiss field, defining and considering behavior of isolated spin subject to magnetic field, and reintroduce you to the concept of molecular or mean field approach. However, instead of that, today I would prefer to speak about spin dynamics. Because somehow what I'm going to say you is also related to quantum information processing, not very directly, but those who are already familiar with something can immediately recognize that the story which I'm going to tell you on a language used by experimentalists and theorists of 20th century and related to the behavior of magnetization or induced magnetization of material subject to time-dependent magnetic field. This is what I'm going to discuss, and this is why I call spin dynamics. We will consider dynamical equation can easily be retold on a modern language of quantum information processing. Just replace magnetization by a qubit, and you replace time-dependent magnetic field by a protocol. However, I don't want to do it right away. I would like to derive and show you some equations, and we discuss at the end what is the connection between what I'm telling you now and what is one of the most hottest topic nowadays in implementation to quantum computing. Okay, so what are we going to do? We discuss no interaction whatsoever. We assume that there is a magnetization which is a vector. It can be magnetization in ferromagnet, or it can be, as I said, even isolated 2-level system qubit. And we say that this classical vector or quantum operator is subject to time-dependent magnetic field. So the Hamiltonian, which we are going to deal with today, is as simple as that. And without losing generality, for most of what I'm going to tell you today, I'll assume that magnetic field depending on T has a constant component, and I will choose my z-axis along this component. This is my choice, and there will be some time-dependent, for the sake of today's lecture, periodically time-dependent component applied in perpendicular direction. So this is a statement of the problem. The magnetization M is connected to spin. So this is G mu bar S. Well, in principle, this is sum over I or J if we are talking about lattice. For the moment, since everything is linear, I will have a superposition on left hand side and right hand side. For the moment, let me drop off, please, but you're late. Question. For the moment, as I said, you will see that I'm going to deal with linear equation. Linear means I can apply summation to the left hand side and right hand side. I will drop summation, and in this sense I will assume that there is only one spin, so to say, or qubit if you like. Yes, this is one of the differences. So, as we discussed it on one of the first lectures, magnetism is quantum phenomenon. So it is related either to existence of quantum number, good morning, which is a spin. I will appreciate if on Friday people come a little bit early, because I find it disturbing. I'm sorry to say that, but those who come 7 minutes according to my clock, and I adjusted it with the computer, after the beginning of lecture, actually disturb and interrupt me. I apologize, but this is really disturbance and real interruption, and I would kindly ask you to avoid it in the future. Thank you. Okay, magnetism is connected to the quantum. Magnetism is quantum phenomenon. So it is connected either to the quantum number of spin, which is spin, or quantization of orbital motion. Today we are discussing quantum phenomena associated with spin quantum number. So in this equation, G is so-called Landau factor, or geomagnetic ratio, Landau factor. I hope that in the course of advanced quantum mechanics you discussed how to sum orbital motion and spin, how to introduce Landau factor. So you know that if I'm talking just about spin, namely the orbital moment is equal to 0, then the geomagnetic ratio or Landau factor is equal to 2. Okay, and mu b is modulus E h bar over 2 mc, is a magneton Bohr, is Bohr magneton. So if I'm talking about nuclear precession, then the mass will be mass of proton or mass of neutron. If I'm talking about electron resonance, m is mass of electron. So since spin is a quantum number, we know that spin operators satisfy commutation relations S alpha S beta is equal to I epsilon alpha beta gamma S gamma. So as it happens many times in quantum mechanics, different components do not commute, so spins are neither fermions nor bosons, and moreover, because of lack of commutation relations, lack of commutativity, so to say, there are commutation relations in certain algebra, it's impossible to measure the moments, all three components of spin simultaneously. You have uncertainty principle equivalent to uncertainty principle associated with non-commutativity of a coordinate and moment. Okay? So, I have a Hamiltonian, and I would like to write down the Heisenberg equation of motion for spin operator. So S is proportional to spin. First of all, let me write down that S alpha dot is equal to I over h bar, and I have a commutator h and S alpha. Okay? So this is my equation of motion. So let me write it down in more details, plugging in this one. So let me proceed with the right hand side. So this is I over H bar. I have a sign minus. And I have M is G mu bar. And then I have H. I will write a scalar product as H beta S beta times S alpha. Where H, this assumes that I have a summation over repeating indexes. So this is minus I H bar over G mu bar, H beta, commutator of S beta S alpha. Yeah. So let me continue that way. So this is minus I over H bar, G mu bar, H beta, and the commutator is equal to I epsilon lambda, epsilon beta alpha lambda S lambda. Okay. I and minus I gives me 1. This is 1 over H bar, G mu bar, epsilon. Let me put it, make a cyclic permutation, lambda, beta, alpha. Now, I will write it as minus, let me say, I will make anticyclic permutation, alpha, beta, lambda, H beta, S lambda. Okay? So this is a cross product, right? This is a cross product, H times S. Namely, its alpha component. So as a result, I will write down that S dot alpha is equal to, if I interchange the order in the cross product, I change sign. Right?
When you change the vis-a-vis, you already should have included another negative sign.
Yeah, well, as I said, I replaced beta alpha, I put minus. Because I times minus I is 1.
There's an initial minus sign at the left side.
Yeah, there is a minus I over H bar. I keep everything. There is initial minus. So this is minus I. From the commutator, it comes I. I to minus I equal to 1. Okay? So, but I would like to write S first. So therefore, I again interchange, and I will write that this is minus times minus, which gives me plus G mu bar over H bar, and this is S times H alpha component. Okay. Then I will multiply right hand side and left hand side over G mu bar. So this is magnetization M alpha dot. I introduce constant gamma, which is G mu bar divided by H bar, which is 2 times modulus E H bar divided by 2 times MC H bar. H bar cancels out. Factor of 2 cancels out. So this is gamma times M H alpha. Or if I remove now index alpha and write a vector here, I have my equation of motion. Okay? I will be dealing with this equation of motion almost all lecture. So the equation says that m dot is equal to cross product of magnetization and applied time-dependent magnetic field. Sometimes in literature this equation is called gyroscope equation. Okay? Good. And this equation, the simplest equation describing dynamics. When I meant linear, of course, I can come back and take summation of i's, summation of lattice side, if I assume that magnetization is associated with a spontaneous symmetry breaking in ferromagnet. So you have net magnetization of a system. Nothing will change because I will add summation over sides here and I will add summation over sides there, and the equation will be the same. Good. Okay, let me now start solving some particular problem. Namely, I will assume that there is a field, constant field, and I choose my z-axis along this field, plus there is a field h1t along x. So I rotate my coordinate frame such a way that this additional time-dependent field, so an h node is along z, will be applied along x direction. As an example, I will consider harmonic field h1t is equal to h1 cosine omega t, just to demonstrate you how the method works. Besides, okay. Let me also write down magnetization M in a way that this is mx ex plus my ey, but then since there is some constant magnetic field along direction, I will write magnetization along z as m node minus mz times ez. So this is z component, just a matter of notation. I would like to define z component that way, where m node is some constant magnetization associated with the fact that it will be total magnetization if we remove periodic time-dependent field from the system. This is the definition of m node. Okay, the cross product m times h is equal to, this is ex, ey, ez, mx, my, mz, h1, 0, h node. Because there is no y component of magnetic field. So if I will write down this determinant, so this is ex times my times h node plus ey, I have mz times h1 minus mx times h node plus ez minus my times h1. Okay? So now I can write down my equation of motion component by component.
Can I ask why in the Because that component of the magnetization is not M0 minus MZ, just MZ.
Oh, that's of course correct. Sorry, you are right. So I should write M naught minus MZ. Therefore, this is MX. Yeah, you're absolutely right. So this is MY times M naught minus MZ times H1 minus MX times H naught, and now it's correct. So I'm writing down equation of motion component by component. So dmx over dt is equal to my gamma my times h naught. dmy over dt is equal to minus gamma mx times h naught plus gamma h1 m naught minus mz, and dmz over dt is equal to minus gamma my times h1. So these are three linear differential equations written component by component. Now I would like to make some assumption in order to linearize these equations. And now you understand why I introduced these notations. So first of all, first assumption, I will assume that H1, the amplitude of periodic time-dependent magnetic field applied along x direction, is much smaller than H naught. And second, therefore, I assume that, you will see that this is true, that therefore all components mx, my, and mz, leave it little m, will be much smaller than m naught. Okay? So therefore, in this system of equations, what should I do? I should drop the terms of higher order. For example, I should drop all terms which contain mz times h1. So therefore, I drop mz here, or my times h1, so I drop term there. As a result, we have a system of equations which reads dmz over dt is equal to 0, dmx over dt is equal to gamma my h naught, and dmy over dt is equal to minus gamma mx h naught plus gamma h1 m. Here h1 depends on t. This is this cosine function. Okay? So, let's look at these equations. First of all, to the last one. It assumes that mz is constant. Okay? Good. I start with the equation of motion for operator m. However, as exercise, please write down equation of motion for operator m square. And show that this equation of motion d over dt m square, which is I over h bar commutator over h with m square, is equal to 0. You can write down the commutator and prove that this is correct. Which means that m square is conserved, and therefore your m square, which is mx squared plus my square plus m node minus mz square is a constant, and of course this constant is just m node square. This is something, some magnetization which occurs along the direction of a magnetic field when I remove time-dependent constant. So your magnetization vector lives on a sphere. This sphere sometimes is called Bloch sphere, but if I plug in the fact that mz is also constant, this equation will give me trajectory in xy space, how described by dynamics of remaining transverse component of magnetization. Okay? So what you will get at the end of the day is a trajectory on a sphere associated with the fact that z component of magnetization is conserved. Good. Let's look at these two equations which I have. Let me differentiate the first equation over time again. So this is d2 over dt square mx. This is equal to gamma h node d over dt my, and d over dt my is equal to this. So this is equal to gamma h node times minus gamma h node mx plus gamma m node h1 t. As we said, gamma is equal to E over mc. Therefore, I will introduce notation omega node square, which is, omega node, which is gamma, which is modulus E h node over mc. So this is Larmor frequency, and therefore I put everything depending on mx to the right hand side. So I have mx double dot plus omega node square mx is equal to gamma m node omega node times h1 t. So what we have actually is equation of motion for harmonic oscillator. So linearized equation of motion for magnetic field describes harmonic oscillator. One side remark is that although the system of equations looks pretty linear, it is in fact contains hidden nonlinearity because the Bloch vector lives on a sphere. So there is a constraint which connects components of magnetic field. So now let me plug in particular behavior. So I will write down that this is h1 times cosine omega t. So I have driven oscillator subject to external periodic force. So this is external force. And as usual, the general solution of homogeneous equation mx is equal to a cosine omega node t plus b sine omega node t. This is a precession with frequency equal to Larmor frequency along z axis, and a particular solution, so particular integral mx tilde should be find in a way c cosine omega t if I assume that omega is not equal to omega naught. Okay. I plug in this particular solution into the linear differential equation, and I will find that c omega naught square minus omega square is equal to right hand side gamma m naught omega naught h1. So this is general. This is particular. So the total solution of my problem mx t should be equal to sum of general solution and particular solution. So this is a cosine omega naught t plus b sine omega naught t plus gamma m naught omega naught h1 divided by omega naught square minus omega square cosine omega t. So if I assume some initial conditions, initial position of magnetization vector in x and y direction, I have linear second order differential equation, or initial position of magnetization and initial velocity, then from initial condition I will define the constants a and b, and then I will find a full solution of my problem. Okay? So this is the way you find general solution, you find particular solution. You have still two constants a and b, so you need two initial conditions, and from given two initial conditions you find magnetization. Good. Just a side remark, what happens if omega equal to omega naught? So if you drive the system with a frequency equal to Larmor frequency, then of course you cannot find solution this way anymore. You can do as following. You can write that this is c, there's a method of undefined coefficients. You assume that this c also function of t, you plug it in, you will find equation for ct, you solve it. Or you can do better, you can opt and subtract the solution with omega naught and apply the L'Hopital rule, and you will find that this particular solution for resonance model is equal to some constant c tilde t times sinus omega t. So the amplitude grows with time, which is true for parametric resonance. Please do it. In a second, I will show you how to solve arbitrary problem with arbitrary driving force using the green function methods. For the sake, I need to discuss the green function of linear differential equation. So let me check that I did not forget anything. Yeah, good. So next paragraph is susceptibility or spin, dynamical spin susceptibility. I will show you that the measurable quantity spin susceptibility is in fact proportional to the green function of a linear differential equation. We will construct this green function, and therefore it will allow to find a solution. So general susceptibility is a response function, which, as we discussed it several times during the course, is proportionality coefficient between magnetization and applied magnetic field. But if you take into account special dispersion and retardation, in the most general way, you can write down that m in a position r and at time t is equal to integral over dr1 integral from minus infinity to infinity dt1. You have a susceptibility chi which depend on R minus R1, T minus T1, and as I said, there is a magnetic field H applied in the point R1 and in the time moment T1. Okay, so you apply magnetic field in some point of a space and at some time, and due to retardation, you find a response in a different point of space and in a different time. So by the definition, so this is a susceptibility. But susceptibility is respecting some retarded properties. Namely, in these integrals, only moments where T1 is smaller than T should be taken into account. Namely, all events in the past. Which means that T minus T1 should be positive. So all moments in the future cannot influence our measurable, right? As we will see, this is a very important condition which defines analytic property of the susceptibility. Okay, so now let's develop. Are you familiar with green functions method? Do you know what is green function of linear differential equation and how to construct it? Does everybody know? Then I will repeat it quickly on example of harmonic oscillator, because we need to discuss the retardation. Yeah. So we have equation which is d2 over dt square mx plus omega naught square mx is equal to some force Ft, external force. Let's define differential operator L, which is d2 over dt square plus omega naught square. So this is differential operator. Then our equation reads L times mx is equal to Ft. And formal solution of this equation is mxt is equal to L minus 1 Ft. So I need to construct the inverse operator. I would like to write down this solution mxt in a spirit of what I said about susceptibility. I would like to write it down as integral over dt1 from minus infinity to infinity. Therefore, I multiply it by the delta function. So this is L minus 1 t Ft times delta function t minus t1. Okay? So since it's a delta function t minus t1, I'm fine to put t equal to t1 in f. I can do it immediately. On the other hand, comparing this with this, I can write down that this is integral from minus infinity over dt1 function g t minus t1 times f t1. Okay? So, I can therefore write down that, so this is L minus 1 times delta function, g t minus t1 is L minus 1 t times delta function t minus t1, or I again apply inverse operator, which says that L t applied to g t minus t1 is equal to delta function t minus t1. So what I'm saying is that the green function of linear differential equation satisfies the differential equation with the same differential operator, but with a delta function in the right hand side. So the delta function is generalized function. You are familiar with that. Now I will solve this equation applying Fourier transformation. So I will write down that first of all I denote t minus t1 equal to tau. I say that g omega is equal to integral from minus infinity to infinity g tau e to the power I omega tau, d tau. The inverse transformation reads that g tau is equal to integral from minus infinity to infinity d omega over 2 pi e to the power g omega e to the power minus I omega tau. Okay? And I use the fact that delta function over tau is just integral from minus infinity to infinity d omega over 2 pi e to the power minus I omega tau. So this is a representation of delta function. Plugging in this g tau into the right hand side, and well, into the left hand side, and applying differential operator, I will get that integral from minus infinity to infinity. Differential operator now will differentiate only exponent. So this is d omega over 2 pi. Omega naught square minus omega square g omega e minus I omega tau is equal to delta function, and delta function is integral over d omega over 2 pi minus infinity to infinity e to the power minus I omega tau. Collecting all terms in the to the left hand side, I find that my green function g omega is equal to 1 divided by omega naught square minus omega square. And in order to find g tau, I just need to take Fourier transform of this function. The power of this method assumes that whatever function I have on the right hand side, periodic, non-periodic, in resonance, out of resonance, if I know the green function, I know particular solution of linear differential equation. You don't need to guess what this particular solution is. You don't need to apply any method. You construct green function once, and you find particular solution of linear differential equation for arbitrary driving of the problem. Okay, now we are in a position to find the Fourier transform. And here, this causality comes. Let's look at complex plane omega. Your function g omega has two poles at omega equal to plus omega naught and omega equal to minus omega naught. So let me say this is minus omega naught and this is plus omega naught. When I take a Fourier transform, I need to I will use a contour integration. For example, if I need to compute this integral for negative tau negative, I have omega equal to omega prime plus I e omega double prime. This is a complex variable. Therefore, minus I omega tau equal to minus I omega prime tau plus omega double prime tau. Sorry. Let me first compute for positive tau. So positive tau means I should have some response. Positive tau assumes that T1 is smaller than T. Therefore, for positive tau, I will close my contour in order to provide a convergence on semicircle into the negative half plane. So this would be contour of integration. And I should get something. However, for negative tau, I should take omega double prime positive. So this is positive tau. And for negative tau, I close the contour this way. And I should get nothing, because my response function should be 0 for negative tau, because our future does not influence our past. Absence of a response when you close the contour in the upper half plane means that there are no poles in the upper half plane, which means I need to take these two poles and shift it down. Then, computing integral for positive tau, I will get something. Computing integral for negative tau, I will get nothing. Which means that in this green function, I should assume that my omega actually is shifted a little bit down such a way that poles move into the lower half plane. And the green function g omega, which is analytic function in the upper half plane. For those who are experts, I can for the moment put letter R, which is acronym for retarded, is 1 over omega naught square minus omega plus I delta square. We already discussed once this plus I delta associated with adiabatic switching on the interaction. This was in the moment when we discussed Linearized function and response dielectric function of metal with a Coulomb interaction. So, what we discuss now is a green function of linear differential equation. However, in condensed matter and in high energy, there is a very powerful tool to deal with many-body interactions, to develop a many-body perturbation theory, which is based on the green functions. Actually, these green functions are not really green functions of some sort of linear differential equations. However, the green function for non-interacting particles is. Therefore, in principle, what I'm telling you has big significance for those who would study methods of field theory in application to condensed matter and statistical physics. Okay, now let me compute the Fourier transform and find the green function in tau representation. Is it clear what I'm doing? And what I'm saying is of paramount importance. So, tau is positive. G tau is equal to integral from minus infinity to infinity d omega over 2 pi e to the power minus I omega tau. And then let me write this one as minus. I will write it as omega minus omega naught plus I delta minus 1 over omega plus omega naught plus I delta. And I need to divide by 2 omega naught. Okay? What I did correct, if I now collect the terms, I will have 2 omega naught divided by omega square minus omega naught square. Therefore, I have this minus. And So I have two simple poles. This is why I did it. So therefore, this is minus 1 over 2 omega naught times 1 over 2 pi. Now I'm closing contour this way in order to compute integrals. I apply the theorems on residues. So the integral is equal to minus 2 pi I, because the contour goes clockwise, okay? And then I have sum of residues. These are simple pole. So the first pole is omega equal to plus omega naught minus E delta. Therefore, this is minus I tau omega naught minus I delta. And the second is minus I tau. It's minus omega naught minus I delta. This is how this integral is computed. So I will cancel out 2 pi. I will cancel out minus. So is I divided by 2 omega naught. However, I would like to multiply by I and divide by I. Therefore, I will put I here, and I will interchange the terms. Those which come with minus will come with plus, because I change overall sign. So what I have here, e to the power I omega naught tau minus e to the power minus I omega naught tau times e to the power minus delta tau. So this is sinus, right? So then this is green function is sinus omega naught tau divided by omega naught e to the power minus delta tau, theta function on tau. And now I can put delta equal to 0. We'll then remove this exponent. Okay, what I did, I found that g t minus t1 is equal to sinus omega naught t minus t1 divided by omega naught theta function over t minus t1. Okay? Therefore, basically, I computed acceptability. So now I write a connection that my solution mx t is equal to integral from minus infinity to t dt1. I plug in the green function of differential equation, sinus omega naught t minus t1 over omega naught. Theta function is already taken into account that I take integral from minus infinity to t. And now I will plug in the force, which is gamma omega naught m naught times h1 over t1. So then, by comparing this equation, I will say that my acceptability chi xx, because this is tensor, and I apply field along x direction, and I compute response in the same direction. So chi xx t minus t1 is equal to sinus omega naught t minus t1 gamma m naught times theta function t minus t1. Or chi chi xx in omega, its Fourier transform, it's equal to 1 over omega node square minus omega plus I delta square times gamma omega node m node. So this is my susceptibility in the Fourier representation. Okay? So I found the response function. So this response function, as I said, is analytic function in half plane. Therefore, it satisfies Cauchy theorem, which is in physics known as a Kramer-Skoronik relation. It satisfies certain causality. Namely, there is a connection between imaginary and real part. The function is complex. Don't forget about I delta. Therefore, let me show you how the imaginary part of susceptibility looks like. An imaginary part of spin susceptibility can be directly measured, for example, by neutron scattering. Basically, all methods to measure response function are based on measurement of the imaginary part, because you will see that the imaginary part looks very simple. And then, using Cauchy theory of Kramer-Skoronik, which connects real and imaginary part, you can restore real part. So this is how people know full response function. So I recall you that if we discussing x plus I delta, so this expression is understood as principal value of x, 1 over x, minus I pi delta function over x. So it has a real part and it has imaginary. So therefore, imaginary part over chi xx omega is equal to, again, I will write down as minus 1 over 2 omega node. So this is gamma omega node m node. And I have take the imaginary part, of 1 over omega minus omega node plus I delta minus 1 over omega plus omega node plus I delta. Using this identity, this is minus pi delta function omega minus omega node. This is minus pi delta function omega plus omega node. I will take overall minus, sign minus out of the bracket. And therefore, I write down that this is pi gamma m node over 2 delta function over omega minus omega node minus delta function omega plus omega node. So the imaginary part of dynamic spin susceptibility consists of two delta functional peaks, resonance. One is at frequency driving clockwise, and another one at frequency driving anti-clockwise. So there is delta function peak at omega node, and there is delta functional peak at omega minus in chi omega. Besides, you will see very important property that imaginary part of susceptibility is odd function of a frequency. So im chi minus omega is equal to minus im chi omega. By applying the same identity to real part, you can show that for real part it's the other way around. So the real part should be even function of omega. But as I say, real part can be recovered from imaginary part using Cauchy theorem or Kramers-Kronig relations, because this acceptability is analytic function is in upper half plane. Good. I deliberately did that, showing you two delta functional peaks, because in the remaining part of the lecture we consider problem with friction, so to say. We will consider the same Bloch equations with finite longitudinal and transverse relaxation time, and you will see that this delta functional peak will be transformed some Lorentz, with Lorentz having some widths, and this width tells us about dissipation in the system. Okay? So, last part of today's lecture will be called Bloch equations. So I hope it's clear, I mean, what was done. So in literature, typically, well, in some literature, the equations without dissipation are also called Bloch equations. But I prefer to use the name of gyroscope equation, because in most of the papers, what people refer as Bloch equation is attributed to the dissipation. So now I assume that spins are coupled to some environment. They can dissipate some energy. And therefore, I will write down the equation of motion of magnetization as dmz over dt is equal to gamma commutator, oh sorry, not commutator, vector product of m times h z component minus mz over t1, where t1 is longitudinal relaxation time, and for transverse components, dm perpendicular over dt is equal to gamma m times h perpendicular minus m perpendicular over t2. So this is longitudinal, this is longitudinal relaxation time, this is a transverse relaxation time. How to derive this equation? Well, in some cases, using some microscopic theory with a Hamiltonian and bath, integrating out bath, one can derive equations of that sort. For the moment, I just postulate that all effects of friction are incorporated into quantities which are 1 over T1 and 1 over T2. Let's first discuss. So this is longitudinal and T2 is transverse. They have a different meaning. Let me first start with longitudinal relaxation time. What does it mean? The longitudinal, the equation for Z magnetization is actually a kinetic equation, because it reads that dmz in this linearized form, dmz over dt is equal to minus mz over t1. One can take microscopic model, derive a kinetic equation, and obtain this equation. So, solution of this simple linearized equation is, of course, mz is equal to some constant e to the power minus t over t1. So let's imagine experiment that we take a Bloch sphere and assume that in initial moment, your magnetization is along x direction. So then the magnetization along z direction is equal to 0. Therefore, at t equal to 0, your mz, which is m node minus mz, is equal to 0. Therefore, your constant is equal to m node, and then mzt is equal to m node 1 minus exponent minus t over t1. Which means that you deflect your magnetization, put it onto equator, and then you turn off your system, turn on your equation, and your magnetization relaxes to z direction, and it relaxes according to this form. This is a kinetic of relaxation of magnetization, which you deflect, how it reaches the direction along. Yeah. And T1 is a characteristic time when the exponent, say, changes by factor. Yeah. Okay, this is what happens with Z component. Let me now go to the transverse component and explain you meaning over T2. Okay, we write down the same equations for oscillators. So then dmx over dt is equal to omega node my. Let me see it here. Minus mx over t2, and dmy over dt is equal to minus omega node mx minus plus gamma m node h1 t minus my over t2. So what I did, I took the same linearized equations which I derived before and add to them the term with 1 over t2. And let me argue that this term, if we translate everything to the language of harmonic oscillator, is just a friction in a harmonic oscillator. So this is a friction in your precession. So how to do that? Again, I will take this equation and differentiate it with respect to the time again. So d2mx over dt square is equal to omega node dmy over dt minus 1 over t2 dmx over dt. Okay, so this is omega node from the second equation. I will write minus omega node mx plus gamma m node h1 minus my over t2. However, I would like to exclude my. Therefore, I use the first equation again. From this equation, my is equal to 1 over omega node d over dt mx plus mx over t2. So therefore, this is this term minus 1 over t2 omega node d over dt mx plus mx over t2, and then I have remaining term minus 1 over t2 dmx over dt. Okay. Now I will collect all term dependent on mx into the left hand side. So what I have? mx double dot minus plus omega node square mx. This is this term. Now I have term minus mx over t2 and another term minus, sorry, I have term minus d over dt mx over t2, and yet another term. So it will give me 2 over t2 mx dot. This is this term and this term, because it's omega naught and omega naught in denominator. And last but not least, I have minus omega naught cancels out 1 over t2 square. So this is plus 1 over t2 square mx is equal to external force, which is gamma omega naught m naught h1. So you see that I have term with mx, this one and this one, and I have term proportional to velocity, which is friction. Okay? So my equation of motion is now equation describing harmonic oscillator subject to some friction, which is dissipation. In order to construct the solution of this equation, I need to construct a Green function and my new differential operator L T is equal to d2 over dt square plus 2 over t2 d over dt plus omega naught square plus 1 over t2 square. And I have to solve the very same equation for construction of the Green function, that L t times g t minus t1 is equal to delta function t minus t1. Therefore, I apply Fourier transform, and Fourier transform of the right hand side gives me 1, and Fourier of transform of the left hand side gives me on the same footing omega naught square minus omega square. I have, you remember that I have minus I omega tau, therefore it will be minus 2I over T2 omega plus 1 over T2 square is equal to 1. Or this is the same as omega naught square minus omega plus I over T2 square is equal to 1. Right? So therefore, the Green function of my linear differential equation Green function omega is equal to 1 over omega naught square minus omega plus I over T2 square. And what you see that I don't need to care anymore about retardation, because the dissipation of friction already provided me that. So instead of playing with this I delta, infinitesimally small deviation from the real axis, now I see that my Green function already correctly describes the system, that both poles of this Green function are in the lower half plane. And the inverse transverse relaxation time, you just characterize me how far these poles are shifted from the real axis. Therefore, I can proceed with the same calculations which I did with delta. And I deliberately kept delta until the very last moment. Therefore, in the calculations which I did before I put delta equal to 0, I can put delta equal 1 over T2, and therefore the Green function T minus T1 is equal to sinus omega naught T minus T1 divided by omega naught exponent to the power minus T minus T1 over T2 and delta function over T minus T1. Okay? That's it. So what I have here, contrast to previous green function was oscillating function. Here I have oscillations and decay. And T2 describes me how fast this green function decays, or T2 is a measure of friction in your precession. Okay. So now I would like to discuss, to do the last thing, and to discuss imaginary part of this green function or susceptibility. So, again, my spin susceptibility chi xx, by comparison what I did before with the green function, t minus t1 is gamma omega node m node times g, t minus t1, and therefore chi xx omega is gamma omega node m node g omega. So chi xx omega is equal to minus gamma omega node m node over 2 omega node, and here I have 1 over omega minus omega node plus I over t2 minus 1 over omega plus omega node plus I over t2. Therefore, I will multiply it, numerator and denominator, by complex conjugated. So this is minus gamma omega node m node divided by 2 omega node. In principle, I can cancel out omega node. What I have here is omega minus omega node minus I over t2 divided by omega minus omega node square plus 1 over t2 square minus omega plus omega node minus I over t2 divided by omega plus omega node square plus 1 over t2 square. Now I can take imaginary part. Imaginary part of chi is equal to minus and minus gives me plus. So this is gamma m node divided by 2 t2, and I have 1 over omega minus omega node square plus 1 over t2 square minus 1 over omega plus omega node square plus 1 over t2 square. At the same time, I can take real part. The real part, you have both. Let me concentrate on imaginary part. Do the same calculations, calculate real part. If we now plot it, first of all, I have a Lorentzian peak at the frequency omega node. Lorentzian peak. The width of this Lorentzian peak on half height is 1 over t2. The height is inversely proportional to t2. And this is something which replaced my delta function. Again, width of the peak characterize you the dissipation. And I have equivalent peak, symmetric peak at frequency minus omega node. As I said, this is precession clockwise and counterclockwise, anticlockwise. And as you may see, that the property that imaginary part over chi xx at minus omega is equal to minus imaginary part chi xx omega is still there. You can explicitly check it. The only question, what happens at small omega? And you can expand this expression assuming that omega is much smaller than omega naught, and you will see that what you will get is linear dependence on of the imaginary part at small frequency. So it's proportional to omega. Actually, this is characteristic behavior for all bosonic system. Imaginary part of your response function for bosonic system, and basically this is density correlation function, should be linear in omega for small omega. We discussed how people measure this dynamics acceptability with neutron diffraction on a single crystal in the lecture devoted to strongly correlated systems. And basically, I'm done with today's lecture. And if you have any questions, please ask.
What is the relation between the correlation of the operators and the green function?
Sorry?
What is the relation between the correlation of operators, quantum mechanics, and the green function?
Well, what people do in many-body theory, they first of all write down Schrödinger equation for psi operator. The green function, so first of all, you second quantize your system. Suppose you have a fermionic system. You have a psi operator which enters the Hamiltonian. The equation of motion for psi operator are Heisenberg equation of motion, well, sort of nonlinear Schrödinger equation, if you like, for interacting system. For non-interacting system, these are linear equations because only interaction brings nonlinearity. The green function is defined as a product of two psi operators taken at different time and different momentum. Therefore, using the equation of motion for the Heisenberg psi operators, you can derive equation of motion for that green function. As I said, for non-interacting particle, this green function is the green function of certain linear differential equation, which is Schrödinger equation for free particle. For interacting system, you then can expand the interacting term using the basis of non-interacting green functions. You proceed with calculations based on non-interacting green functions, and the beauty of this method, known as Feynman diagrams, is that you have possibility of resummation of certain class of diagrams. For example, you can replace a bare green function, which is defined on non-interacting particles, to the bold green function. You can replace the interaction by dressed interaction, and so on and so forth. And recently, this method developed by Feynman in 50s, 60s for high energy physics, and then utilized in condensed metaphysics. Now people have even more benefit from it, applying it to diagrammatic Monte Carlo. So diagrammatic Monte Carlo is a powerful method which allows to generate certain order of diagram, dress it using bold diagrammatic Monte Carlo, and actually solve reliably. So sum up to millions of diagrams, which is of course impossible analytically. You can proceed with few orders of perturbation theory. If you're lucky, you can second order. If you spend years of your life, you probably can do it correctly in third or fourth order. But Monte Carlo provides you opportunity to do it on a computer. So in a sense, this is one of the most powerful approaches nowadays to solve strongly correlated systems, certain strongly correlated systems, because first of all, for quantum Monte Carlo, for fermions, there is no so-called sign problem. There is what people call sign blessing. And on the other hand, there are also powerful tools of resummation and analytic continuation of results which are converging inside the circle of convergence to the outside of domain of convergence. So this is nowadays one of the hottest topics in modern computation in application to strongly correlated systems. Because as I said, certain strongly correlated models, especially in 2 and 3 dimension, Hubbard model, Heisenberg model, Condé lattice model cannot be solved analytically. However, the numerical tools, and in particular those who are based on diagrammatics and use of green function, actually produce a lot of progress in understanding of phase diagram of this system, which is important for high temperatures, for conductivity and other things. Okay, today you will see something on quantum information processing, but basically I think the speakers will discuss of implementation of certain quantum protocols for spins or systems in optical lattices or outer cold gases on one hand, and then utilization of these protocols in quantum computations and quantum information processing. So how to manipulate with the 2-level system, with a qubit or system of coupled. So one 2-level system or one spin 1/2 is a qubit, regardless how you made it. You can make it out of superconductors, for example. This is one of the ways. One can make a qubit with outer cold gases. However, for reliable quantum computations, one needs to have a system of several qubits. For certain problems, 10 is enough, but then there should be protocol of manipulation of error correction codes. And the gentlemen who got a Dirac medal and who will be awarded today made very important contribution to the development of quantum protocol and quantum manipulation necessary for quantum computations. Okay, we are done, and yeah, we need Friday. Okay.